So my name is Sylvia Gradacek, and I'm Associate Professor of Materials Science and Engineering at MIT. And my research focus is on synthesis of materials with confined dimensions and their applications in nanophotonics, nanoelectronics, as well as in energy conversion and harvesting. In my group, we work on synthesis of nanostructured materials and their applications. But what is really missing in that path is really understanding how, by changing the composition and the structure of the materials, we tune their properties. And for that reason, we put a strong emphasis on development of the characterization tools on the nanoscale. And what that means is that we are developing a special type of characterization methods that enable us to measure the composition, morphology of the materials on the nanometer or even on the atomic scale, and then directly correlate this with the other properties of the materials, including optical properties. So many conventional techniques that are currently being used in research that are focused on understanding the optical properties of the materials have resolution that is on hundreds of nanometers or even micron scale. And this is really limited by the sources of the light and excitation that is used to understand the property of the material itself. And we are putting a strong emphasis on development of so-called electron microscopy techniques that enable us to see materials on the atomic scales. We can identify the composition and the position of a single atom within the material. And then by knowing how the position and the composition of the material is changing on the atomic and nanometer scale, at the same time we have the ability to control and study and detect optical properties of the materials on a similar length scale. So instead of measuring the optical properties on the nanometer or micron scale, now we have the ability to squeeze this down to nanometer scale. And why is this important? The reason why it is important is because when we do deal with nanostructured materials, very often we are looking into optical properties of a single nano object that has the scale of a couple of nanometers. So if you apply conventional techniques to understand their properties, then you're typically observing or investigating an assembly of these materials, meaning that you're looking into hundreds or thousands of nanocrystals, and then you're getting the response from this entire assembly. However, very often we are interested in the properties, whether it's an optical or mechanical property of a single nano object. So by developing these particular types of characterization techniques that are based on electron microscopy, we now have the ability to study individual nano objects. And this is particularly exciting if you want to understand and control the properties of nanomaterials for future applications. In terms of understanding what are the current challenges in implementation of materials that are nanostructured for different types of applications, there are a couple of important things to consider. One thing is that we are still learning how precisely to synthesize these materials. For example, for a given type of application, we need particular type of a material. So let's say that we need what is the composition, what is the size, what is the morphology of that material that we need to develop. There are still certain challenges in understanding how to control these properties in situ during the growth. And this is exactly what we are trying to learn in my laboratory. How during the synthesis, what are the knobs that we need to tune in a way to design or develop the material for a particular application. Another challenge in future development of the nanostructured materials for a variety of applications is understanding how to scale something that is developed in the laboratory to large scales. For example, we are developing flexible solar cells or light-emitting diodes that are based on new type of nanostructured materials, but they're typically in the sizes of centimeters or 1 square inch. However, their applications will require large scales. One of the current challenges is how to scale something that is being developed in the laboratory and to the sizes that are applicable to the real-life applications. And this transition is sometimes not trivial. For example, we are developing certain types of methods how to deposit nanomaterials on different type of electrodes, but the question how to transfer that from a very, very small scale to something that is on the large scale and still preserve the quality of the material such that we can preserve the efficiency of the devices is one of the challenges that we will need to address in future.